Let us see how we can simulate the DC-DC converter interfacing the PV source and the load. Earlier we saw how to make the PV source, the symbol and the sub-circuit, and we will use that PV source to power up the DC-DC converter and deliver power to the load R0. We shall simulate the PV source DC-DC converter in open loop. We will just have a PWM. We will still not close the loop, which we will come to later after having discussed the MPPT tracking algorithms. So what we can take up for simulation is the PV source. We can have a PWM and the DC-DC converter. This shaded region we will simulate in SPICE. In the simulation folder, I have created 4 more folders. The boost folder for simulating the boost converter interface to the PV module, buck boost converter interface to the PV module, the buck converter, and there is an M file here in this folder which will check for reachability of the duty cycle for any given converter. Let us look at the boost converter first. I have here the schematic file. Let me zoom that. Yeah. Now you see that this is the schematic of the boost converter, inductor, switch, diode, capacitor, load. So this portion is the boost converter. I have a capacitor here across the terminal of the PV to improve the ripple, input ripple. This is the PV source module, the model of which we designed earlier. pv.sub is the subcircuit file which contains the subcircuit model of these and few others. It also contains the model for this power switch. It also contains the model for this PWM. I have here a voltage source which is set to a value 0. Voltage source set to a value 0 can be used for sensing the current through that branch. So VIPV is sensing actually the PV current IPV, and VIL is actually sensing the inductor current. This is also a current sense voltage source, value set to 0. I have put some initial condition values on the energy storage elements. Capacitance, I have this initial condition. Inductance, I have this initial condition 1.8 amps. And capacitor also, I have put this initial condition 49.5 volts at the output, so that the simulation will be smooth and fast and you will not see a lot of oscillation during the turn on process. So for this R0 of 100 ohms, I have calculated that the VC value should be 0.44 to give a duty cycle of 0.72. What is the relationship between duty cycle and the VC voltage? Let me just show you. Boost converter and the PWM block here. Now VD is setting actually the duty cycle. So inside the PWM block there is a triangle carrier, something like this. So let us say the triangle carrier is going plus minus in this fashion. This is -1, this is 0, this is +1. So if VD value is at -1, then duty cycle is 0. At VD here in between 0, then the duty cycle is half, which is 0.5, and at VD is equal to +1 along the tip, D is equal to 1. So therefore we get the relationship D duty cycle is VD plus 1 by 2. The PV source we know what is the value of short circuit current and the voltage scale value, and we have simulated the PV source and seen the IV characteristic. So you know the short circuit current value and the open circuit current value and also the peak power point value. So using those values we can calculate what should be the value of T. In the PV sub-circuit file, we have power underscore SW. This is the sub-circuit for the power semiconductor switch. So the power underscore SW is the sub-circuit for this power semiconductor switch. This PWM triangular PWM is the sub-circuit for this block here, PWM single phase, where we have as parameter the carrier frequency, and then if you go further down you have the PV source. The sub-circuit PV source is the one that we made earlier, and that is for this XPV, the PV source. Now let us go to the terminal and simulate this circuit. I have opened the terminal. Let me go to the folder, boost. I will generate the netlist boost.net using gnetlist. Execute that. Now go into ngSpice. ngSpice boost.cir. So it will perform the simulation, and then we have this one. Now let us plot. What do you want to plot? I could plot the input current VIPV into the voltage, terminal voltage, that will give the power. So let us plot VT, terminal voltage, into current through the VIPV source, the IPV sensor. So you will see that the input power is hovering around 26 watts. You saw earlier that this PV module that we used had a peak power of around 26 watts. So at this particular duty cycle, it is presenting an optimum RT value, terminal resistance, as seen from the PV module, such that maximum power gets transferred. We shall observe the waveform here at the input to the PWM. You see that it is 0.44 or 440 millivolts that we had set, and at this value the duty cycle is 0.72. How did we get this duty cycle of 0.72? Again, from the relationship. Let me show you how. Let me go into this M file. I will open this reachability.m file. It's an Octave script file. So you see here, I am making R0 vary from 1 to 100, and this is the characteristic of the PV module that we have used. It's a 26 watt panel, 14 volt VM, voltage at peak power. IM is calculated PM by VM, RT is VM by IM, the terminal resistance. Then for every value of R0, we execute this, and what do we find out? we find what is the duty cycle for a boost converter. Using that relationship RT, which is equal to R0 1 minus D whole square, find that the duty cycle for the boost converter is 1 minus square root of RT by R0. Like that you can do for the buck converter and the buck boost converter also. And I will present the results onto the Octave workspace. So let us open Octave and run this, and let us see what happens. So let me have Octave. Let me go to the M file where you have reachability.m, and let me clear this workspace screen and type in reachability. So you see here that we have the PV source details listed here. Voltage at peak power 14 point, current at peak power 1.8, terminal resistance peak power 7.6 ohms. Now here, first consider column 1 only. R0, this is R0. For every value of R0 load resistance, we have some value of duty cycle for the boost. You see, these are not valid duty cycles. Now let us see. For R0 of 100, we see that the value of duty cycle is 0.72 to achieve peak power operation according to this equation at peak power point. So 0.72 duty cycle would mean VC of 0.44 using the relationship that we just saw for the PWM triangle, which is going from -1 to +1. So that is why we had kept the VC value at 0.44. Let me now change the R0 value from 100 to something lower, let us say 70. At 70, the duty cycle is 0.67. That corresponds to 0.67 into 2 minus 1, which is 0.34. So instead of 0.44, we can change it to 0.34. But first, let us change the R0 value from 100 to 70. So let me alter the value of R0 to 70. Now let us run the simulation. After running the simulation, I expect now that the input power coming out of the PV panel will not be peak power. So it will be much less than that. So let us view that. You will see that, the peak power was at 26 watts. Now it is lower, somewhere around 23 watts. Now let us say if we give the matching duty cycle of 0.67, then will the power come back again to peak power operating. So now let me alter VC to 0.34. This corresponds to a duty cycle of 0.67. So let me change that. Now let me run the simulation again. So now the duty cycle is matching with the R0, and therefore the RT presented to the PV panel would be optimum, that is at peak power operating point. So we expect the power drawn from the PV panel to be at the peak power point. So you see here that the panel is now back to supplying 26 watts. So in this way, you can try to understand the various aspects of the circuit, try to observe the various currents and the voltages of this boost converter interface to the PV panel, and try to get as much insight as possible. I will leave it to you to work out with as much detail as possible and as much variations as possible for this boost converter circuit that I will also be sharing with you in the resources section. Let me now go into the buck folder and open the buck.schematic sh file, and let us zoom this, and you see it is similar to what we discussed in the boost converter, only now this is a buck converter. You have the switch here, the inductor and the L with a freewheeling diode in this fashion. You have the same PWM, then you have the VC control voltage. You have the XPV, this is the PV source, is the same PV source, ISC2 V scale 20. So now therefore let us simulate this. What should be the value of duty cycle? I have put it at 0.62 for an R0 of 5 ohms. How do we find this value of duty cycle? Let us run the reachability check and then find out the values. So you will see here, for the value of R0 5 ohms, the duty cycle for the buck converter is 0.81. For the boost converter it is an invalid duty cycle, can't use it. For the case the buck converter, it is 0.81. So that will work out to be 0.62. 0.81 into 2 minus 1, which is 0.62. So given this, let us save, go to the terminal, and let us simulate the circuit. First let me generate the netlist using gnetlist and then ngspice buck.car. So the simulation goes through, and we would like to observe the input power, the power out of the PV panel. So let us check that out. You see that it is now hovering at around 26 watts, which is the peak power point. You can cross check, plot the voltage, the control voltage. It is at 0.62. What happens if I set R0 to 20 ohms? At 20 ohms, the duty cycle required is 1.62 for the buck converter, which is an invalid value. The duty cycle should be between 0 and 1, and therefore you will not, if R0 is 20 ohms, you will never be able to achieve peak power. However, at the given same value duty cycle, if you put R0 as 20, the power drawn will be very less. For example, alter R0 to 20, and the duty cycle control voltage VC is still 0.62. Run, and you will see VD is same, still 0.62. And let me plot the input power. You see the input power has dropped below 10 watts, which is really poor. On the other hand, let me change R0 to 2 ohms. 2 ohms, where the duty cycle for the buck converter is 0.51. So let us say I change alter R0 to 2 ohms. Run the simulation. You see that it is much lesser than the peak power point. However, if I change the duty cycle to 0.51, see, let's say 0.5, 0.5 corresponds to 0 volt VC. So let us say 0 volt VC, and then rerun the simulation. Alter VC to 0, run, and again if I look at the power, you see that it is back again to delivering peak power. So you can always match the duty cycle with the load, and by trying to match the duty cycle with the load such that RT, the terminal impedance seen at the terminals of the PV module, is such that it is placed at an operating point which will give maximum power. I will leave it to you to further explore this buck converter circuit and try to get more insight out of it. Let us now look at the buck boost converter interfacing the PV panel to the load. So let us go into this one and open the schematic of the buck boost converter, and let me zoom it like this. Yes, so this is the buck boost converter. Observe that there is a switch here in line with the input. You have the inductor and the diode in this polarity. You see that the inductor will freewheel through the diode in this fashion. The voltage across the capacitor is negative. Now, same PV source we have used. So this is ISC at 2 amps, V scale 20. Same as before, rest of the circuit similar. I have CT here, the terminal capacitance acting as the energy storage buffer, PWM 10 kHz, and the VC control voltage deciding the duty cycle. I have set it at 0.56. Again, from the relationship, reachability relationship. One advantage with the buck boost is that for the buck boost, the entire range of the IV curve is reachable, and you will see that all are valid duty cycles. Now take for example the octave output. See that here this last column here is the duty cycle for the buck boost, and if you go through you will see that all the duty cycle values are valid values, which means every duty cycle value is reachable. Now for the 100 ohms load R0 that we have put, the value of the duty cycle for the buck boost is 0.78. So 0.78 into 2 minus 1, 0.56. So therefore we have set the VC value at 0.56 to give the peak power point. So this is like before, a sub-circuit power underscore SW, the power switch, and we have the PWM triangle. Now let us simulate this circuit for 100 ohm R0 and the VC value set in such a way that duty cycle is 0.78. So let me open the terminal, and I will use gnetlist to generate the netlist for the buck boost schematic. So you do that, and then I will use ngSpice buckboost.car. So it will now simulate, and after that is over, I would like to observe the input power. So you will see that the input power, you will see here hovering. See that this is hovering over 0.26 watt, which is the peak power point of the panel. So you see that there is a lot of ripple in the current. This is basically because of charging discharging of the capacitance. You see that there is this input capacitance, storage capacitance that we have put. One may have to adjust this value to get lesser ripple or higher ripple. So that is why this ripple is present here. Now let us say that I go right down in R0. Let us say we'll take this R0 of 8 ohms. For R0 of 8 ohms, in the case of the buck boost, you have 0.50 as the duty cycle. So when you express it for VC, it will be 0. So let me first alter the value of R0 to 8 ohms from 100 ohms and then run the simulation. And after running the simulation, let us observe the input power. The input power is way below the maximum value. It is settling down somewhere to a very low value, even below 10. So let me now observe that the duty cycle voltage is at around 0.56 or 560 milli as the value, control voltage value. Let me adjust it to this value, what is supposed to be 0.5 duty cycle, which means VC of 0. So I will alter VC to 0 and then run the simulation, and you should see that the input power is brought back to the peak power point value, because now we are given matching duty cycle such that RT is at the appropriate load line angle slope. Now you see that the power is back again to close to the peak power point. So I will leave it to you to explore this circuit also and try out various things, and try to visualize observe various waveforms, visualize the waveforms, and try to understand the circuit with the PV source being the input source with the IV characteristic as given. You can also explore with different values of short circuit current and the voltage scale values and try to see what happens. This will give you more insight into interfacing the PV panels to the load by means of a switched mode DC-DC converter. Right now we have done the simulation of this entire PV panel DC-DC converter load combination system using a PWM block, and it is an open loop. VC is just a fixed value, it is not closed, the loop is not closed. So this is just to ensure that in under open loop is the system okay, well designed and working as per our expectations.